Hey everyone, so today we're going to be doing section 3.7, which is over marginal analysis in business and economics. So our goal is to understand marginal cost, revenue, and the profit function. Marginal cost, revenue, and profit. So an important application of calculus is the economics side. So if you're thinking about going into business, you're definitely going to be studying some calculus. When we talk about a marginal change, it is referring to a rate of change, which would be similar to a derivative. So if I want to talk about something like C prime, which would be the marginal cost, that represents the instantaneous change of the total cost. So it would be like, what is the change in cost if I'm going from producing 200 units to producing 201 units? Likewise, we can do marginal revenue, which would be our change in revenue, and our marginal profit, which would be our change in profit. So this section, there's not a whole lot of new content, but rather application of what we have learned and the business world. So to get started, just a couple different terms that are used in economics. We have our total cost function, which would be C of x. Our marginal cost, which would be C prime of x, our total revenue, R of x, marginal revenue, R prime of x, total profit, and profit is defined as revenue minus cost, so P of x is R of x minus C of x, and then the marginal profit, P prime of x, equals R prime of x minus C prime of x. So a few things to clarify before we get started. If we're looking at the cost, revenue, or profit function, for example, C of x is not, it represents the total cost of producing X items, not the cost of producing a single item. So for example, the total cost of producing X plus 1 items would be C of x plus 1. The total cost of producing X items would be C of x. So if I wanted to know what is the exact cost of producing that one extra item, it would be C of x plus 1 minus C of x. Example 1, a company manufactures fuel tanks for cars. The total weekly cost in dollars of producing X tanks is given by C of x equals 10,000 plus 90x minus 0.05x squared. And part A asks us to find the marginal cost. So remember, marginal means take the derivative. We want the derivative of our cost function. So C prime of x, the derivative of 10,000 is 0. The derivative of 90x is 90. And then the derivative of negative 0.05x squared is going to be 0.1x. For B, it says find the marginal cost at a production level of 500 tanks per week. So we're looking at what is C prime of 500. So this would be 90 minus, let's see, 0.1 times 500 is 50. So that's 40. So we have a marginal cost of $40. So what that means is that our estimated cost of producing an additional unit is about $40. So for part C, they're asking us to find the exact cost of producing the 501st item. So they're asking us to find C of 501 minus C of 500. So this is kind of similar to the last section with differentials. Part B is giving us the approximate cost of producing an extra unit, where C is going to give us the exact cost. So to do C, I'm going to get my calculator out, and I need to plug in 501 and 500. So C of 501 is going to be 10,000 plus 90 times 501 minus 0.01, or 0.5, sorry, times 501 squared. It looks like I forgot to put a parenthesis in there, so let's try that again. 90 times 501 is going to give us 4,000, or 45,090, and then I need to subtract 0.05 times 501 squared. That's going to be minus 12,550.05. And if I do that, I'm going to get 32,539.95. So now I need to do C of 500. C of 500, if I plug in, I'm going to get 32,500. So if I take the difference, I'm going to get 39.95. So that is the exact cost of producing my 501st item, where according to B, my estimated cost is $40. So we're off by a nickel, but that is a very good approximation. Example 2. A company manufactures automatic transmissions for cars. The weekly cost in dollars of producing X transmissions is given by C of X equals 50,000 plus 600X minus 0.75X squared. So for A, it says find the marginal cost function. So again, remember, marginal means take the derivative. So we're looking for C prime of X. The derivative of 50,000 is 0. The derivative of 600X is 600. Minus the derivative of 0.75X squared is going to be 1.5X. For B, it says find the marginal cost at a production level of 200 transmissions per week. So they're asking us to find C prime of 200. Well, that's going to be 600 minus 1.5 times 200, that's 300. So 600 minus 300 would be 300. So we're looking at a change in cost of about $300 to produce an additional transmission. For C, it's telling us to find the exact cost of producing the 201st item. So they're asking us to solve for C of 201 minus C of 200. So to do this, I'm going to have to plug into the original function, C of X. And let me get my calculator out. So it's going to be 50,000 plus 600 times 201. And then I'm going to subtract 0.75 times 201 squared. When I do that, I'm going to get 140,299.25. So this is my C of 201. And then when I do C of 200, I'm going to get 140,000 and exactly. And then when I take the difference, I should get 299.25. So this is $299.25. So the approximation was 300. The exact answer is 299.25. Again, if you were giving someone an estimate, telling them that the price would be about $300 and it coming out to be 299.25 is pretty accurate. To help illustrate why our estimated cost and our exact costs are very similar, we can take a look at example 1 again. So we know that the difference between the approximation and the actual cost was only 5 cents or 1 nickel. And this is exactly what's going on. We have our cost function, that's this curve right here. And then we have our tangent line, and this is our approximation. The difference between the approximation and our actual cost would be this line here. And you can see it gets bigger as we get further away from that point. As in, when our difference, our delta x, gets smaller, our approximation and our actual answer are getting very close. So when delta x is 1, we're just changing production by 1 unit. We're going to see that our approximation is very close to our exact answer. This slide is just reinforcing the previous one. It's telling us that our marginal cost, our C prime of x, is very close. It's approximately the exact cost, especially when x is large and delta x is small. So the application is that we can quickly come up with what our approximate change in cost, revenue, or profit is without having to get a calculator out and do some intense calculations. This can help us tell if the demand for an item is high or low, if we need to continue production, reduce production, or maintain a consistent production. And we're going to see all sorts of examples like that throughout this section. So this is going to be a long example. There are multiple parts to it, so I can only fit the prompt on this page, but we're going to have to use a lot of information. We're going to be flipping back and forth. So I'm going to make sure to keep all relevant information on future slides. So it says that a company's market research department recommends the manufacturing of making a new headphone set for an MP3 player. After suitable test marketing, the research department presents the following price-demand equation, where x equals 10,000 minus 1,000 p, where x is the demand at price p. And sometimes here we get a little bit of confusion. We use a capital P for profit and a lowercase p for price. So if you got bad handwriting like me, capital P and lowercase p tend to look the same. So I'm going to do my best to make sure that they are different. So if we want to solve for price, all we're going to do is, we're going to have to try to isolate P here, but we're going to get P equals 10 minus 0.001x. So as the demand goes up for my headphones, the price for the headphones go down. So a cost function for manufacturing the headphones will be 7,000 plus 2x. This is provided to me. And they're saying the 7,000 is the estimated fixed cost. So think about tools, overhead, rent on the facility, where $2 is the estimated variable cost per headset. So think about the materials, labor, transportation, and all that. So I've got a price and I've got a cost. So continuing our problem, for A, it says find the domain of the function defined by the price-demand equation. So if we take a look at the price, we said it was 10 minus 0.001x, where P is the price and X is our demand. So to try to find a domain, in theory, there is no restriction here. X can be any number, and then P would be, the output. But in reality, we do have a restriction on our price. We don't want the price to be 0 or a negative because we want to charge something for our item. We don't want to give it away for free. We also don't want to pay people to take it away. So we know that P should be greater than 0. And in theory, we want our demand to be limited to 0 also. Having a negative demand would be a bad thing. So we're taking a look at when P, we don't want our price to be 0, we don't want our demand to be 0. So I'm going to put 0 is our lowest X value we'll accept. And then for a top end, what value of X would make P equal 0? Well, we could say, well, let P equal 0. So we get 0 equals 10 minus 0.001x. So 0.001x equals 10, which gives us that x equals 10,000. So we know that our demand is somewhere between 0 and 10,000 if we want to work in a realistic scenario. For B, it wants us to find the marginal cost, C prime of x. So C of x, that was 7,000 plus 2x. So c prime of x, the derivative of 7,000 is 0, the derivative of 2x is 2. So c prime of x is just 2. And then for c, it wants us to find the revenue. And it says that revenue is equal to price times demand. So remember, price was 10 minus 0.001x, and demand is just x. So if I multiply price times demand, p times x, I'm going to get 10x minus 0.001x squared, and that would be my revenue. So my revenue is 10x minus 0.001x squared. So continuing on to part D, it says find the marginal revenue at 2,000, 5,000, and 7,000. So remember, marginal means derivative. So r prime of x, and just a reminder, r of x was 10x minus 0.001x squared. So r prime of x is 10 minus 0.002x. And to find the marginal revenue at x equals 2,000, 5,000, and 7,000, all we have to do is plug in. So r prime of 2,000 is going to be 10 minus 0.002 times 2,000 is 4. That gives me 6. R prime at 5,000, well, it's going to be 10 minus 10, which equals 0. And r prime at 7,000 is going to be 10 minus 14, which equals negative 4. So before we move on to E, let's just think about that. So the marginal revenue is talking about how my revenue will increase if I increase production. So r prime of 2,000 is positive 6, which means that approximately for the next unit that I make, I will bring in another $6 in revenue. So if you were in charge of manufacturing, would you want to increase production, keep production the same, or decrease production? I would say, hey, if I'm making another $6, let's just keep producing. If we look at r prime of 5,000, we get an increase of 0. So at that point, would you want to increase production, keep production the same, or lower production? And at 5,000, if my next unit's gonna cost or bring me another $0, in that case, it's not worth making another unit. I would want to halt production. And when r prime is 7,000, we get 10 minus 14, which is negative 4. So in this case, every additional unit I'm making, I'm gonna be making less money. I'm bringing in negative $4, which means that I would definitely want to lower my production. So at 2,000, it's definitely increased production. At 5,000, it looks like keep production the same. And at 7,000, it says slow down production, we're making too much. Now for part E is going to take up quite a bit of room. So I have the next slide also dedicated to part E. So E says roughly graph the cost function and the revenue function in the same coordinate system and find the intersecting points of the two graphs. So this is where it takes a little bit of work. And having a graphing calculator would definitely help. So my revenue function is going to be a downwards parabola. And I know that I'm starting at 0, 0. And I'm ending at 10,000, 0. This was the domain of my function. Now I'm going to have the cost function. My cost is linear. It's 7,000 plus 2x. So this was my revenue. This is my cost. And they're asking, where did these 2 points meet? So that's asking, where is revenue equal to cost? When does revenue equal cost? So they're asking, when is 10x minus 0.001x squared equal to 7,000 plus 2x? When are these two guys equal to each other? And that's what we're going to solve on the next slide. So it's still part E, but I'm trying to find what these 2 points of intersection are. So where we left off, we had that we wanted our R of x to equal our C of x. So our revenue was 10x minus 0.001x squared, and that was going to equal 7,000 plus 2x. So I want to get everything to the same side and equal to 0. So if I move everything to, let's say, the right-hand side, I'll get 0 equals 0.001x squared minus 8x plus 7,000. Now, there is a pretty easy way to solve for x here, and it's going to be back in our algebra. We got to use the quadratic formula. Unless you're really good at factoring, you might be able to come up with something to factor here. But this would be my a term, this is my b term, and this is my c term. So remember, the quadratic formula says it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So when I start plugging in, I'm going to get that x equals positive 8 plus or minus negative 8 squared is 64 minus 4 times a times c. So 4 times a times c is going to be 28. 0.001 times 4 times 7,000 comes out to be 28. And then I'm dividing by 2 times a, so that's 0.002. So going on, this is 8 plus or minus the square root of 36 over 0.002. So that's 8 plus or minus 6 divided by 0.002. So if I do minus 6, 8 minus 6 is 2, divided by 0.002 is 1,000, so x is 1,000. Or if I'm doing plus, I get 8 plus 6, which is 14, divided by 0.002, which is 7,000. So as we saw from our rough sketch, we do know that the graph intersects twice, and it's at x equals 1,000 and at x equals 7,000. Here is the graph provided by our textbook, which if you take a look, it is similar to what we were looking at in our rough sketch. We do have the downwards parabola, which is our revenue. We've got our linear function, which is our cost. The points where they're even, this is at x equals 1,000 and x equals 7,000. So we got that part. And they kind of break this down. They say where the cost equals the revenue, this is called your break-even point. It means that you're not making any profit because your revenue was equal to your cost. You didn't lose money, but you didn't make money. So in these regions over here, they're saying that this is a loss. That means your cost was more than your revenue. You're spending more than you're making. You're losing money. But then you've got this sweet spot in the middle. This is profit. This is where you're making money. And we know that profit is defined as revenue minus cost. So in our next part, they're going to be talking about the profit function. So we're going to be talking about revenue minus cost and trying to figure out where do we make the most profit? Is it where we make the most revenue, or would it be at another point? So F wants us to find the marginal profit at x equals 1,000, 4,000, and 6,000. So profit, P of x, is equal to revenue, R of x, minus C of x. So we've got to recall that our revenue is 10x minus 0.001x squared, and our cost was 7,000 plus 2x, but because I'm subtracting cost, it's going to be minus 2x. So this is my profit. I can clean this up a little bit. I'm going to write the x squared first, so it's 0.001x squared. 10x minus 2x is going to be plus 8x, and then minus 7,000. And this will look familiar from when we were about to use the quadratic formula. all the signs changed, but that's because when I did the quadratic formula, I was doing cost minus revenue. Here it's revenue minus cost, so the signs changed. But this is my profit function. This is my P of X. So if I want to take the derivative, because I want the marginal profit, P prime of X is going to be negative 0.002X plus 8. And from here, all I have to do is plug in 1,000, 4,000, and 6,000. So P of 1,000, or P prime of 1,000, negative 0.002 times 1,000 is negative 2, plus 8, which is positive 6. So when I produce 1,000 units, if I continue production, my profit should go up by $6. Not bad. Let's check out P prime of 4,000. P prime of 4,000, if I plug in 4,000, I should get negative 8 plus 8, which is 0. So at P prime, it says if I continue production, I am not going to make any more money, no more profit here. And then at 6,000, P prime of 6,000, I'm going to get negative 12 plus 8, which equals negative 4. So this says if I continue production, I'm going to make $4 less. I'm going to lose $4 in profit. So again, if you were in charge of increasing production, keeping production the same, or decreasing, at 1,000, we would say increase production. If we continue to produce, our profits go up. At 4,000, we would say halt production. We're at our optimal position. If we continue to manufacture, we're not going to make any more money. And at 6,000, you would say reduce manufacturing, because if we continue, we're going to be losing money per unit. So our revenue was maximized at 5,000, but our profit is maximized at 4,000. And that's something important to note. So we do have one more concept for this section, and that would be the marginal average cost, revenue, and profit. So we've talked about marginal cost, revenue, and profit. We've talked about cost, revenue, and profit. But now we want to talk about average. So this is saying, how does the average cost change as we increase production? How does the average revenue change as we increase production? And how does the average profit change? So to find average cost, they call it C bar. They just put a bar above the C. All you do is divide by X. Divide by the number of units you're producing. So to find average cost, it's your total cost divided by X. And then to find the marginal average cost, you take its derivative. For revenue, same thing. If we want to find average revenue, it's R of X over X. And to find the marginal average revenue, you just take the derivative. And profit, same thing. If you know what your profit is, divide by X, that's your average profit. To find the marginal average profit, take its derivative. So the important thing is that you take the average first. So you don't want to take the derivative and then divide by X. You divide by X and then take the derivative. And that's probably the number one mistake I see people make, is that they will take the derivative first. They'll get the marginal cost, and then they'll divide by X and hope that that's the marginal average. But you need to take the average first, then take the derivative. So an example here, it says that a small machine shop manufactures drill bits used for the petroleum industry. The manager estimates that the daily cost in dollars of producing X bits is 1,000 plus 25X minus 0.1X squared. So for A, it wants us to find C bar and C bar prime, which would be your average cost and your marginal average cost. So C bar, the average cost, we just divide every term by X. So we're going to get 1,000 over X plus 25X over X minus 0.1X squared over X. And we've got some reduction. The 1,000 over X, I'm going to write that as 1,000 X to the negative 1. 25X divided by X is 25. And then 0.1X squared divided by X is going to be minus 0.1X. So to find the average marginal cost, we take the derivative of that. This will be negative 1,000 x to the negative 2 minus 0.1. You can leave your answer like this, but if we're going to have to compute, it might be easier to move that x squared to the denominator. So this is going to be negative 1,000 divided by x squared minus 0.1. And in B, they want us to plug in 10. So they say find the average cost of 10 units and find the average marginal cost of 10 units. So C bar of 10, we're plugging into C bar over here. So this would be 1,000 over 10 plus 25 minus 0.1 times 10. So that's going to be 100 plus 25 minus 1. So we get 124. So the average cost of producing 10 drill bits is $124 a drill bit. So if we were to increase production, let's say we're trying to make like an 11th drill bit, how much would that bit cost? So we're looking at C bar prime of 10. So this would be negative 1,000 over 10 squared over 100 minus 0.1. So this would be negative 10 minus 0.1, which would be negative 10.1. So we're saying that if we were to increase our production by 1, the average cost of a drill bit would decrease by $10.01. And this makes sense. As you mass produce, the average cost tends to go down. That's why people mass produce things. So if we wanted to estimate what our average cost would be, that's what they're saying in part C, is we know that right now our average cost is $124. And if I were to increase production by just one drill bit, we would expect to spend $10.1 less per drill bit, giving us a new average cost of $113.90. This is our predicted new average cost if I were to use 11 drill bits instead of just 10. So we've got our closing thoughts here. I hope that made sense. There's not a lot of new content other than maybe some business terms. And we just wanted to see a general application of calculus. I know that calculus can seem like a very abstract subject, but it really does have real-world applications, usually in business and economics and in the STEM field. So if you go into like physics, chemistry, engineering. So this is just one aspect. People tend to understand dollars because we use money all the time. So hopefully this is giving you some insight on the real applications of calculus. Again, the homework should be posted, and if you've got any questions, just let me know.